Well, students, in the third chapter of our course, we have so far introduced direct methods and iterative methods for linear systems. In this lecture, we will talk about errors in the solution computed by those methods. And we will also introduce a method called residual corrector method. Let X star denotes the computed solution using some method, then obviously the error involved in X star when compared to the exact solution of the linear system AX equal to B is defined by this vector. That is, E is equal to X minus X star, and we call this error as mathematical error. Why we give this special name? Because there is one more error which is involved in the computation, that is called arithmetic error. So in order to distinguish arithmetic error from the error committed by the method, we give the special name mathematical error. By mathematical error, we therefore mean only the error committed due to the approximation of the model, that is the error involved in the numerical method. Whereas otherwise, it is assumed that there is no other error involved, something like arithmetic error or human error. More precisely, the arithmetic error is not involved when we are talking about mathematical error. And similarly, when we are talking about arithmetic error, the mathematical error is not taken into account. When we combine these two, then we will call it as total error. But in this section, we will only talk about the mathematical error. Suppose I want to know what is the error that is involved in my computed solution, that is the mathematical error, then I need to have two things. One is the approximate solution that I computed from my method, and another one is the exact solution, right? But practically seeing, we will not be having exact solution in hand. We will only be having the approximate solution, that is the computed solution in this case. Therefore, practically, mathematical error is not possible to obtain. And if we can obtain mathematical error, it means we have exact solution. When we have exact solution, then the natural question is, why are we going for computing the approximate solution for the system? Therefore, in that sense, there is no meaning in asking for the mathematical error directly from this formula. Now the question is, can I get the mathematical error without knowing exact solution? That is the interesting question. As long as you are working with linear system, it's nice to know that we can get the mathematical error without knowing the exact solution. That may sound a bit surprising, but let us see how to do that. For that, we have to introduce another type of error, which is called the residual error or the residual vector. I'll tell you why we call this as a residual error. First, let us define it as residual vector, and it is defined as the difference between the right-hand side vector and the left-hand side quantity, that is AX, but instead of X, we put the computed solution X star. This is called the residual vector, but often it is also called a residual error. Why? Because if you put X in the place of X star, then you can see that R is equal to 0, right? Because we are solving the system AX is equal to B. Therefore, if you replace X star by X, then AX is precisely B, and therefore R is equal to 0. That is something similar to E also. If you replace X star by X, then you get E is equal to 0, right? So in that sense, we can also view R as an error, but it is not precisely the mathematical error that is defined in this form, but it also resembles its important property. That is why often we call residual vector as residual error. Okay, keeping this in mind, let us see how to obtain the mathematical error E without knowing the exact solution X. Let us start with the residual error R. By definition, it is B minus A into X star. Now, B can be written as AX and the second term is retained as it is. Now, since A is a matrix, which is a linear transformation, you can write this term as A into X minus X star. Now, what is this? This is nothing but A into E, right? Therefore, the vector E, which is unknown when the exact solution is not known to us, and that unknown can be obtained as the solution of the system AE equal to R. Observe that once you have the computed solution X star, then R is explicitly known to us. Therefore, you can plug that R as the right-hand side here, and you can solve this system in whatever way you solve. Assume that you are solving this system exactly, then what comes out is the exact solution of this system, which is nothing but your error vector E, and that is obtained without knowing what is your exact solution. Remember, this luxury is there only for linear systems. Why it is so? Because in nonlinear equations, this step will not go through, right? Therefore, such a luxury cannot be expected in the nonlinear case. That is when the equation is nonlinear. Suppose you are working with f of x equal to 0. This is the equation I am working with. As long as a is a linear function, you can enjoy this property. But if f is nonlinear function, say if it is x squared plus 2x plus 1 equal to 0, then f will not satisfy this condition, right? Therefore, in general, we cannot compute the error, that is the mathematical error, without knowing the exact solution. But in the linear case, yes, it is possible via the residual vector. The next concept that we are interested in is the stopping criteria. In the iterative methods discussed so far, we see that a sequence of vectors is generated by these methods, whether it is Jacobi method or Gauss-Seidel method or any other method which we did not discuss. As long as it is an iterative method, it generates a sequence of vectors that is expected to converge to the exact solution of the given linear system, right? It may not happen in general, but our wish is that that sequence should converge. It means what? The sequence terms xk will tend to the exact solution x only as k tends to infinity, right? In general, it may happen that if you find the distance between xk minus x, it may not be equal to 0 for all finite k, right? But if you go on taking terms larger and larger, then this distance may shrink to 0. Theoretically, it is very clear, but computationally, how will you get the exact solution? Because your computer cannot go on computing the solution lifelong, right? If you are going to achieve your exact solution only in the limiting case, that is k tending to infinity, it means on a computer, you will keep on finding the terms after terms, and there is no end for that. So on a computer, we have to stop at some finite k, say k naught, and declare that x of k naught is, well, not exact, but approximate solution for our system, right? Now, the question is, what is this k naught? That is, what is that finite term that I should stop so that I can declare the corresponding iterative term as my approximate solution? See, this you cannot decide manually, but there should be a criteria for you so that your computer program will decide once that criteria is achieved. Now, what is the best criteria that you can apply so that your computer program terminates the iteration computation and declares that the last iteration that it computed is the approximate solution for your system? How will you decide that? Well, a very natural idea is to go for finding the norm in some norm, say L1 norm or L infinity norm, or even Euclidean norm. At the norm level, it's not difficult to compute the Euclidean norm on a computer. Therefore, you can go for the Euclidean norm itself. The most natural condition is to compute the norm of your mathematical error, and you define some number, say epsilon. It can be, say, 10 to the power of -5 or something you fix a priori, and then check after every iteration whether the mathematical error is less than that epsilon, right? This is the most natural and convincing condition that one can think of. But obviously, as we told in the previous slide, this is practically not possible, because to compute this, you need to know exact solution. If you know exact solution, then naturally the question is, why am I putting effort to find an approximate solution for that? Therefore, this condition is, although very convincing and the most efficient way of stopping your iteration, practically it makes no sense to go for this stopping criteria. Therefore, the question is how to decide where we have to stop our computation of the iteration. In other words, how do we know whether the computed vector xk at the kth iteration is sufficiently close to the exact solution or not, is the question now. Of course, there is a very good clue from our previous slide that residual error may be a good choice for us. So you can use residual error or residual vector at every iteration, and then you see if the residual error is less than your epsilon that you defined previously, right? Once that is achieved, then you stop the iteration. So this stopping criteria works very well for linear systems. However, it may be dangerous to use this idea as a stopping criteria for nonlinear equations, but that we will discuss in the next chapter. But in this chapter, since we are dealing with linear systems, this is a very good criteria to stop your iteration. Next, let us discuss residual corrector method. When we use a computing device for solving a linear system, irrespective to whether we use direct method or iterative method, we always get an approximate solution, right? Just now we have seen that an attractive feature of linear systems is that the error involved in the approximate solution when compared to the exact solution, that is the mathematical error, can theoretically be obtained exactly by solving the linear system AE is equal to R. Remember, theoretically, we can obtain E exactly by solving this system. However, when you go to put this system on a computer and use any method, even direct method, we are not going to get exactly the value of E, right? There is one more added problem in solving this system. The problem is that as you go closer and closer to the solution, your approximate solution AX will be in such a way that AX star will be approximately equal to B, right? That is, when X star is very close to your exact solution, consequently, your AX star will be very close to the right-hand side vector B. And if you recall, your residual vector is the difference between B and AX star. Therefore, you are coming across the subtraction of two numbers which are very close to each other, and therefore this will lead to a loss of significance. And hence, when you use this vector r as a right hand side to obtain the mathematical error e, then there is a danger that you may significantly magnify the error in the mathematical error while computing the solution of this system. So to avoid this, one has to use a higher precision in computing the solution of this system when compared to the precision used for obtaining x star by solving this original system. For instance, if b and ax star, in particular x star, are calculated with say n-digit rounding, then it is preferred to use 2 n-digit rounding while computing the right-hand side vector r, and consequently while computing the error e by solving this system. So that is the idea. So again, I will summarize. Assume that you obtained x star using a n-digit rounding. Then use 2 n-digit rounding in calculating r, and also in the calculation of the solution of this system AE is equal to r. Then only you will have a reliable value for the mathematical error E. Let us illustrate the computational procedure of the residual error in this example. Consider the system given by this. We are interested in finding the solution of this system using 4-digit rounding approximation. That is, at every arithmetic operation, we do the 4-digit rounding of both the inputs as well as the computational result. One can see that if you use an infinite precision calculation, then round the solution to 4 digits, then you get this as the solution. So this is the true solution for your system, but shown here after rounding to 4 decimal digits. Now let us compute the solution of this system using Gaussian elimination method without pivoting. Using 4-digit rounding, it means at every calculation you do a 4-digit rounding. Then the solution is given by this. The solution is good when compared to the exact solution up to 4-digit rounding. But still, let us go to compute the error involved in the approximate solution when compared to the exact solution up to 4-digit rounding. To do that, you have to use 8-digit rounding arithmetic. So first we have to find the residual error with 8-digit rounding, because the basic solution was found using 4-digit rounding. So you have to double the precision for finding the residual error, and also consequently to find the mathematical error by solving this system, you have to use 8-digit rounding. As per this, you will get this as the mathematical error up to 8-digit rounding. Note that up to 4-digit rounding, the error is given by this. So we know the exact solution up to 4-digit rounding. We also got the approximate solution using Gaussian elimination method. Why it is approximate? Because we did a 4-digit rounding calculation for that direct method. Although it has the capacity to give exact solution, but it is only in the infinite precision. Since we used 4-digit rounding, therefore, x star obtained from the Gaussian elimination method is still an approximate solution, and the mathematical error involved in x star when compared to x up to 4 digits is this, whereas this error is obtained by solving AE is equal to R, where R is obtained using the formula B minus AX star with 8-digit rounding. That is more important. And then we used again Gaussian elimination method, now with 8-digit rounding, and that gave us this value. One can see that your E star is again pretty close to your mathematical error. Now, once you have a good idea of what is the mathematical error that is involved in your solution, Now the question is, why can't I add that to say x star star is equal to, I'll have x star, which I computed using Gaussian elimination method or any method that you would like, plus you put this E star also. That will be a better approximation to your exact solution when compared to x star, right? So that is the idea behind residual character method. So let us propose this idea as a iterative procedure. First, by predicting the error by solving this system with 2n rounding or chopping, if n digit rounding or chopping is used in the approximate solution, and then correct the approximate solution x star by adding the predicted error with the vector x star, as I told previously. Let us do it systematically. Take your x star as x naught. How are you obtaining it? Well, you obtain x star using any method that you prefer. It can be Gaussian elimination method with or without pivoting. It can be some LU decomposition method, or it can be even using Jacobi or Gauss-Seidel or any other iterative method for some n number of iterations. Whatever may be the procedure, finally you got an x star. Now the residual character method can be used to further improve the accuracy of x star. That is the purpose. In that, what you do is first you take x star as your initial guess. You have used n digit rounding or chopping. Then you go to find the residual vector of x naught and call that residual vector as r of 0. Remember, that has to be done with double precision. Once you get r naught, you again solve this system to find E naught. And once you have E naught, then define x1 as x naught plus E naught. Obviously, we expect the vector x1 to be more closer to the exact solution than x naught, right? And once you have x1, again go to find r1 and then plug in r1 as the right hand side and solve the system A E1 equal to R1. That gives you E1. Once you have E1, you add that E1 to X1 and call it as X2. So let us present the general procedure now. Assume that you have calculated Xk, the kth iteration, then your k plus 1th iteration is defined as xk plus ek, where ek is obtained as the solution of your linear system aek equal to rk, where rk is the residual vector of xk. So this is the procedure. Whatever precision you have used to obtain x naught, you should use the double of that precision to further correct your error. Okay, that is the only key point that you have to remember when you are working with this method. This method is called the residual character method. As I told you, you have to use higher precision than the precision used for computing x naught precisely. So what you should do is x naught is n digit, rk and ek are done with 2n digit precision. It can be either rounding or chopping. And once you have this, again, character procedure k plus 1 is equal to xk plus ek should be done with n digit. That is, once you get ek, you round it to n digit. You will be having 2n digits in ek. You round it to n digit and then add it with xk. Therefore, xk plus 1 will have n digit in the mantissa. And when you go to find rk, you have to use 2n digits. And consequently, ek also should be done with 2n digits. And the iteration should go on like this. Let us do an example. Assume that you have solved this linear system using Gaussian elimination method with pivoting using 4-digit rounding. In that way, you got an approximate solution to this system, which is given by this. This is just for our information. But for our residual corrector method, we are given a initial guess like. Now we have to start from this initial guess and do the residual corrector process to obtain a better solution than x naught. Better in the sense that after each iteration, the vector xk should be more closer to x than the previous iteration. That is the idea. So for that, what we have to do first is to find the residual vector. To find the residual vector, we have to keep a higher precision. Now, what is the precision that we have to fix for this problem? As I told previously, it is 2 times the precision used in representing x naught. You can see from here that x naught is represented with 4 digits, right? Therefore, you have to do the calculation with 8 digits. Well, whether we obtained this by 4-digit chopping or rounding, that will be given as an information to you in the question. Like I may ask you to use the residual corrector method and improve the accuracy of this vector using 3 iterations and use rounding. So if you say like that, it means you have to do rounding calculation. But how many precision? Well, that information you will get from how we have represented x naught. Here we represented x naught by 4 digits, and we said that you perform 3 iterations using rounding. It means the residual error has to be obtained using 8-digit rounding, and from here you have to obtain the error vector again using whatever method we prescribed. Here I am asking for the Gaussian elimination. Similarly, we may also say that perform 3 iterations and rounding and use, say, Jacobi or Gauss-Seidel or any other method, including Gaussian elimination. Here we are doing Gaussian elimination. Therefore, you have to use 8-digit rounding calculation in Gaussian elimination with pivoting. Again, I'll tell you how you are getting 8-digit. That I will not tell explicitly. You have to get that information from the way x naught is represented. But rounding, I will tell you explicitly, and which method you have to use in obtaining the mathematical error will also be told explicitly. Whereas the number of digits you have to get from the way x naught is represented. Here x naught is represented with 4 digits. Therefore, you have to use 8 digits. And that gives you the mathematical error as the solution of this system, whatever method you use. Here we use the Gaussian elimination with pivoting. And once you get this, then your x1 is represented as x naught plus e naught. Remember, we would have got this e naught with 8-digit precision, but in order to add it with x naught, we just put it with 4-digit rounding, and then you add it with x naught, and that you call as x1. Again, what you will do for the next iteration, you will compute R1 with 8-digit rounding arithmetic, and from there you will again solve this system. AE1 is equal to R1 again with 8-digit rounding arithmetic using whatever method we asked for. Here we used Gaussian elimination method with pivoting. And once you get E from this system, you make 4-digit rounding of that, and then you go to do x2 as x1 plus E1. Again, this calculation is done with 4 digits. So you got x2 and you keep on going like this. So in this case, we got x1 as x0 plus E0. Remember, E0 is also rounded to 4 digits. X0 is already given in 4 digits. Therefore, you will get x1 in 4 digits. Again, from there, you will get R1. To get R1, you will be doing the 8-digit rounding. Then you will get E1. Sorry, this is E1. E1 you will get in 8-digit. While doing the computation for E1 using any method, you will do 8-digit rounding. And the final answer, which you get as a solution of your system, that final answer will be rounded to 4 digits. And that is how you will get E1 here as 4 digit. And that will be added with X1 to get X2 as 4 digits. And keep on going like this until the number of iterations asked for. Suppose if you are asked for 3 iterations, then you may have to do one more.